Okay, continuing our work with continuous random variables, and in this video we're going to move from the mean/expected value via some analytical work by hand and some graphics calculator work. We're going to move to variance and hence standard deviation. And the video will culminate for expressions that describe variance and standard deviation, such as that one, for example, there. And we're also going to recap a few bits of what we talked about with the mean of a continuous random variable. Just conceptually, the difference between mean and variance. Mean is talking about the center of the data or typical values. And variance is talking about the distribution or the spread of the data across the distribution. And these are pairs of graphs. There's a pair there and a pair there. We can see that on the left-hand side, the graph is really talking about the effect of the mean, because the distributions here in these this pair of graphs here on the set of axes, the blue and the red, they have the same spread or the same distribution in every way except for the mean. The mean is clearly different, and you can see how that creates two distinct peaks. On the right hand side we have two graphs that have the same mean, but their distribution, the spread of the data, is notably different. And that's one way of contrasting these two measures. And perhaps before now you've looked at in various studies of stats two types of statistics, basically. The center, the central tendency, things like that, the mean, and you might have seen the median and the mode previously, and variance. Well, even if you haven't heard variance before, you perhaps have heard of standard deviation, interquartile range, or even just the range. So we're looking at things like that, but we're sticking to the mean, variance, and standard deviation for a continuous random variable x. A little bit more formally now, the variance of a random variable x is a measure of the spread of the probability distribution. So it's one way of measuring, coming up with a metric to talk about how a probability distribution is spread. And it's about the mean, all right? It's focused about the mean. How's it spread around the mean? Is it spread widely? Is it spread more narrowly? A bit like what we were discussing here. Okay, the blue is spread differently around the mean compared to the red curve. And just remembering from our previous work that the random variable is called capital X, and the expected value or mean, one of the symbols for that is mu. Another way of looking at the variance, it's considered to be the long run average. In the long run, the average value of the square of the distance from x to mu. Alright, so ultimately what's the square of the distance from x to mu, where x is the variable, okay, for each part of data, to mu the mean. So how far away is everything from the mean squared? Okay, now the squared tends to be something that is there to get rid of the negative quantities, because some things are above and below, okay, to have an absolute positive value. Variance, thus, if you square something, the units are not the same. There's the squared units of what you had before. So that leads us on to the next part, which is a simple step. If we want the same units as what we had that we were measuring with the function and the mean, we take the square root. Hence, to find the standard deviation, once we've found the variance, we just take the square root. Perhaps you've seen that before. So in this formula here, SD of x is the standard deviation of the random variable x. There is a proof that connects the forms you see below, but that's beyond the scope of this video. And so you can see that variance can exist in various forms. Perhaps you might see something like this on a formula sheet, but we can develop that using these other two handy formulas. You can probably see a real similarity between the last two formulas there. They're very similar, aren't they? Let's have a look at how all that works. And it's helpful if you can link this to some of your prior studies, for example, discrete probability distributions, because you would have seen those formulas, the last two for the variance before. Three things to do. We're going to find the expected value, the variance, and then the standard deviation of the random variable x, which has this probability density function. So the first step is stuff we've done before. So I'm going to do that quickly, but also going to show the role of technology in order to do the same thing as we can do analytically. So it's good to be across both things, both realms. So we start by writing down the generic formula here for expected value or mean. And in this case, because of the piecewise nature of it, the bottom function contributes nothing. So we look at the first part, and more specifically, we can see that it's limited by 2 and 0, or 0 and 2, and we have x times, instead of p of x, it's called f of x, function f, that's no problem, but x times 0.5 x dx, and we move on. We've got 0.5 outside of the summation of these. Oh, I forgot to write down my, notice how I forgot to write down my x there. Okay, so I was looking for an x squared, and there it is. And that's what we're integrating now. And I'm going to change the 0.5 to a fraction 1/2, and this x squared will be x cubed over 3, which is a third, so a half of a third is a sixth. So I've moved that denominator of 3 outside, which by now you should know you can do. And we've got 1/6 outside of 8 take 0, which is 1/6 times 8, which is 4 on 3. Let's see if we can get the same thing with technology. Okay, so typing in, you can see on the left hand side of the keypad, so I'm literally just going to type in define, and then I'm going to put in f of x there, then enter the equal sign, you literally just type in the equal sign, not the enter key. I might elaborate on that. And then use your template for a piecewise function with two functions, which is that one there, and we enter in what we need. We have 0.5x, and that's between 0, and you got your inequalities over here. Okay, whoops, that jumped down to the next line, and try again. X and 2. It's done it again, it likes to jump down there. And 0, and a good way to do that is else, because that does the job. And then we hit enter. That's defined. So now we take the integral that we're after from 0 to 2, and so one way of doing that is numerical integral, like so, and all that just gets entered in, and you've got that there, 1.3 recurring. Then optionally you can go to the number menu and approximate to fraction, and you got 4/3, but I think you knew that was 4/3, just the calculator terminated the decimals at 5 places there. So much is our answer. Now for the next part, the variance. So there's our selection of formulas for the variance, okay, according to the definition of the variance. We can use the method of composition of functions that we saw in the previous video on that work that was an extension on expected value. So we need, again, particularly in this formula, we need these two values here. Now be careful, you should see these from your work in discrete distributions, discrete variables, e of x squared minus e of x all squared, okay? So be careful to get those right. Alright, so writing that down, and remember from the previous step, the 4/3 right there, that's e of x, okay? So e of x all squared that thing that we're trying to find there is 4/3 squared. 16 on 9, in other words. So that step was easy. Now for e of x squared, which we covered in the previous video, it's composition of functions. So e of x squared is, instead of x times f of x, or p of x dx, it's x squared by f of x in the integral. Okay, and in this one, as we said before, is active between 0 and 2, essentially, for our purposes. And so we've basically got, when we integrate, we need to use the actual function, so that needs to be written in explicitly, so it's x squared. Now that was times 0.5x. Okay, so the 0.5 or the half, I'm going to put that out there, and the x part just stays in there. So we've actually got x cubed, really. So we've got a half times the integral between 2 and 0 of x cubed dx, which is pretty easy to integrate. And continuing on, we will have x to the power 4 over 4. I'm going to put the over 4 bit out here, and that's between 0 and 2. So that's effectively 1/8 times 16 inside the brackets, and that's 2. So we're nearly ready. We can put all this into the formula here. I'd recommend that you remember this one. Alright, it may not be on your formula sheet, even though it's related to something that is on the formula sheet. Remember that one. Okay, so that's my little tip there. Remember that formula. So, the variance, therefore, putting it all together, is, now we said it's e of x squared, and we said that's 2, you can see it there, and take away e to the x all squared, which was 16 on 9. So 18 on 9 take 16 on 9 is 2/9. Alright, so that's whatever it is, units squared, whereas that's just units, whatever. It might be kilograms or something, centimeters, whatever. Alright, this is an abstract question. So the standard deviation is the last part here, standard deviation of x. Didn't mean to make a square bracket there, I'm sorry, I just got distracted by a knock at the door, but it didn't do anything. And so that's a square root of 2/9, which is root 2 over 3, and it's back to the original units. Haha. If you're a nervous type, you might need it in decimal, so you can sleep at night. But that's it.